Right now, your device is actually silently running these hidden text files that essentially hold the entire operating system together.
Yeah, it's all happening entirely out of sight.
Exactly. And the crazy thing is, a single typo in just one of them has the power to permanently wipe your hard drive in milliseconds.
It's terrifying when you really think about the sheer power there.
It really is. Welcome to our deep dive. Today's mission is to completely demystify the shell script. We're drawing a really comprehensive Wikipedia analysis that breaks down how these seemingly simple text commands automate entire architectures.
Right, and the decades of evolution behind them, too.
Yeah, and of course that unforgiving power they put in the hands of whoever happens to be typing. So if you want to understand the invisible mechanisms executing behind that blinking cursor of a command line, you are definitely in the right place.
It's going to be a fun one.
Okay, let's unpack this. A shell script fundamentally just acts as a wrapper, right? It isn't a compiled application at all.
No, not natively. It's really just a plain text file.
Right, containing a sequence of commands that, sets up an environment, executes a payload, and handles the cleanup.
Yeah, I like to think of it as the connective tissue of an operating system. Because instead of a user sitting at a terminal, just painstakingly typing commands one by one.
And waiting for each one to finish.
Exactly, waiting around, evaluating the output manually. A shell script captures that entire operational logic into this repeatable, automated sequence. You're effectively writing a blueprint.
A blueprint that the system's command interpreter, which is the shell, just reads and executes from top to bottom.
Precisely.
But before we dive into the operational logic, we really have to look at how the operating system even knows what to do with this text file in the first place.
Right, because the script is just plain text.
Yeah. There are no compiled binaries telling the processor what to do, and the secret lies in the very first line of the file with this weird character sequence called the shebang.
The shebang, I love that word.
Right. It's a hash sign followed immediately by an exclamation mark.
And the shebang is just a brilliant piece of system design. Because, in standard shell syntax, a hash sign denotes a comment.
Meaning it tells the interpreter to just ignore whatever follows because it's human-readable documentation.
Exactly. But the kernel of the operating system, the core of it, looks specifically at the first 2 bytes of an executable file.
Oh, wow. So it checks before anything else even runs.
Right. If it sees that hash and exclamation mark together, that shebang, it intercepts the file before a standard text parser ever touches it.
Okay, that makes sense.
And it treats the rest of that first line as an absolute path to the specific interpreter required to run the code below it.
So if you write #bang/bin/esh at the top of your file, the kernel explicitly routes all the subsequent text through the Bourne shell.
Exactly.
And this leads to a mechanism in the source that completely shifts how we think about file formats. Because of the shebang, shell scripts do not actually need a .sh file extension.
They don't need it at all.
The system relies entirely on that internal first line. It completely ignores whatever letters you put after the dot in the file name.
Yeah, the extension is basically irrelevant to the machine.
But wait, if the operating system doesn't need the .sh extension, why is it so ubiquitous? I mean, is it strictly a psychological comfort for developers to categorize their files visually?
Well, what's fascinating here is that deliberately avoiding extensions actually serves a profound architectural purpose.
Really? Like what?
Seamless reimplementation. When you deploy a utility without an extension, you completely decouple the tool's interface from its underlying technology.
Okay, I'm following.
So imagine a development team creates this complex network diagnostic tool written as a shell script, right? And they simply name the executable netcheck.
No extension, just netcheck.
Right. And then operations teams build their own automated workflows around typing that exact command, netcheck.
And then, say, 2 years later, the network scales up, and the original shell script becomes this massive performance bottleneck.
Precisely the scenario. The engineering team realizes they need to rewrite netcheck entirely in C++ or Rust to handle the new performance demands.
Oh, I see where this is going.
Yeah, because they never appended a .sh to the original file name, they can just drop the newly compiled binary right into the system, overwriting the old script.
And the file name just remains netcheck.
Exactly. The end users and all those surrounding automation systems never have to update their workflows. They keep running the exact same command.
Completely unaware that the underlying machinery was completely swapped out.
Right. The shebang handled the routing invisibly in the first version, and the compiled binary handles itself in the second.
That is an incredibly elegant way to future-proof system utilities.
It really is.
So, okay, the system knows how to read these files, and we understand how to deploy them cleanly. Let's transition into how scripts actually alter our interaction with the machine.
Moving from manual inputs to generalized automation.
Yes. The source provides this classic example using the else command, which lists directory contents. You can write a tiny script named simply L, literally just the letter L.
A great shortcut.
Right, and inside you configure Ls with a highly specific environment variable. LC underscore collate equals C.
Yeah, LC collate equals C. That specific variable forces the system into traditional byte-wise sorting.
Because by default, a lot of modern systems use these complex locales that fold uppercase and lowercase letters together when they're sorting files, right?
Exactly. By forcing it to C, you guarantee strict ASCII sorting. It ensures hidden dot files and capitalized system files are grouped exactly where a developer expects them.
Rather than just scattered alphabetically among all the lowercase user files.
Right, which can be super frustrating.
And the script doesn't just stop at sorting either. It appends a very cryptic string of characters at the end of the command. It's, quote, $ at symbol, end quote.
Yes, the magic parameter string.
It looks like accidental keyboard mashing to me. But the source notes it is absolutely crucial for passing parameters.
It really is. It is the mechanism that preserves the integrity of user input.
How so?
Well, when you run your new GRUL command and add arguments to it, say you want to search a specific folder named annual report, the shell needs to pass that argument to the underlying ULS command.
Right.
If the script just blindly pasted your text, the space in annual report would cause the shell to split it into two separate arguments.
Oh, right. So it would search for a folder named annual and then a totally different folder named report.
Exactly. But by using that, quote, $@ quote parameter, the script tells the shell, hey, take every extra argument the user provided and pass them along while strictly preserving their original quotation boundaries.
So it maintains the exact structural intent of the user.
Precisely.
That same philosophy of capturing intent applies to the ./build script example in the text too.
Oh, the classic build script.
Yeah, decades ago, compiling a C program might require typing out like 4 distinct compiler commands in sequence.
Which is incredibly tedious.
So instead, developers wrap those steps into a single script. You just pause your coding, type ./build, and the system handles the sequential execution.
Yeah.
Now, I know the source notes that dedicated build tools like Make eventually superseded this specific practice in the 1980s.
They did, and for a very good reason. Tools like Make evaluate dependencies.
Okay, break that down for us.
Well, a basic shell script will just recompile every single C file every time you run it, which wastes massive amounts of processing power.
Right, just doing the whole job from scratch.
Exactly. But a Make utility checks the timestamps of your files. It only recompiles the specific modules that have actually changed since the last build.
Okay, that distinction highlights the true nature of shell scripts then.
Yeah.
They aren't really meant to be specialized dependency tracking engines.
No, they are generalized orchestrators.
Right. You write a script to convert images, you feed it a wildcard like star.jpg, and it just processes an entire directory autonomously.
You shift from being an active participant chained to the keyboard waiting for each image to convert to a high-level manager who kicks off a batch job and just walks away.
Yeah, it's like a fundamental paradigm shift in computing.
It absolutely is. A batch job breaks the synchronous relationship between human and machine.
You're not laying individual bricks anymore.
Right, you are handing the finalized blueprint to the foreman and trusting the automated processes to execute the construction unattended.
I love that analogy. But if these scripts are looping through directories, evaluating wildcards, orchestrating other programs, we really have to look at the boundaries of what this actually is.
You mean, is it really programming?
Yeah. Does this level of logic cross the line from just scripting into full-blown programming?
The source confirms that scripting is unequivocally a subset of programming.
Okay.
You're writing code that dictates conditional logic and system behavior. Modern POCX-compliant shells and their extended counterparts are incredibly robust.
Yeah, the source mentions they natively support if-then control flows, while loops, array structures, and even callable subroutines.
They support all of that, yes.
Yet they still have severe hard limits by design. The text specifically points out their lack of data typing, classes, threading, and complex math capabilities.
Right. In a shell script, practically everything is treated as a text string by default.
So if you try to do complex floating point mathematics, The shell just struggles because it isn't designed to handle precise numerical types natively.
Exactly. It forces you to rely on external utilities to do the math and then pass the string back to the shell.
Okay, so that lack of native data typing is exactly why you wouldn't write a physics engine or a massive database system in a shell script.
No, definitely not. The shell is not the heavy lifter. It is the foreman coordinating the specialized heavy lifters.
And looking at the lineage of these foremen is honestly like reading a genealogy of the digital age.
It's quite a family tree.
It is. The source details the original Bourne shell SH, which actually inherited structural concepts from the AlGOL programming language.
Giving it that procedural block-structured feel.
Yeah, and from there, the family tree just explodes. You get GNU Bash, the Z shell, the Debian-Almquist shell, or Dash.
Dash is great because it strips away all the bloat for pure performance.
Right. And then you have modern non-POSIX shells breaking the traditional mold entirely, like the Python-centric Sanch or Microsoft's object-oriented PowerShell.
But what all of these interpreters share is their fundamental role as glue code.
Glue code, yeah.
And to really unlock their power, they constantly embed specialized Unix text processing tools, specifically SED and awk.
Okay, explain how those fit in.
So the shell manages the files and the processes, right? While SED streams through the text, making surgical replacements, and awk acts as a programmable filter, extracting specific columns of data from logs.
Here's where it gets really interesting. The source points out that this specific combination of tools eventually hit a critical mass.
Yes, the birth of a new language.
Exactly. Developers were constantly piping data back and forth between the shell, awk, SED, and C programs.
There's a lot of juggling.
And eventually, the friction of juggling all those separate utilities inspired the creation of the Perl programming language.
Which is huge.
Yeah. Perl essentially absorbed the system management capabilities of the shell, the regular expression power of awk, and the structural syntax of C into a single cohesive language.
If we connect this to the bigger picture, the evolution of Perl illustrates the classic life cycle of software development.
How do you mean?
Well, shell scripts are the ultimate prototyping environment.
Okay.
Why? Because the syntax you use in the script is literally identical to the commands you type directly at the terminal.
Ah, so there's zero cognitive friction.
Exactly. A developer doesn't have to switch mental gears into some abstract object-oriented language just to automate a quick system task.
There is no compilation step, no heavy IDE required. You just open a text editor, write the logic, and run it instantly.
And that immediacy makes shell scripts the crucial first draft of modern software. You mock up the complex sequence of system interactions, debug it interactively on the command line, and prove the logic actually works.
And then?
Once the concept is validated, and if the execution speed becomes a bottleneck, the engineering team rewrites that proven logic into a compiled language like C or Go.
That makes total sense. But that raw immediacy, the ability to interact directly with the operating system without any safety nets or compilation checks, that brings us to the dark side of shell scripting.
Yes, the danger zone.
Because you are executing commands with absolute system authority. A single typographical error doesn't just crash an app, it can annihilate the entire environment.
The command line is a famously unforgiving space. It assumes the user knows exactly what they're doing and executes instructions with ruthless literalism.
The source highlights a terrifying piece of Unix folklore that perfectly illustrates this. The arm-arf*/typo.
Oh, the legendary typo.
Right, so to understand the mechanism here, we need to break down how the shell parses wildcards. The command R means remove.
And the flags -R and -F tell it to recursively delete folders and to force the deletion without asking for human confirmation.
Exactly. No, are you sure? Prompts. Now imagine a developer wants to delete everything in all the subdirectories of their current folder. They intend to type arm-arf*/ with no space before the slash.
That command would successfully target only the local subdirectories.
Right, but if their thumb grazes the space bar, inserting a single space before that slash, they type *//
A tiny mistake.
But the shell evaluates wildcards before it ever hands the arguments over to the marm command.
This is the crucial part.
So the shell looks at the asterisk, expands it into a list of every single file in the current directory, and then it looks at the slash, which represents the absolute root directory of the entire hard drive.
Yes.
And it hands both of those targets to the remove command.
And the ROM utility dutifully accepts the parameters. It deletes your current files, and then it systematically erases the entire operating system, from the kernel down to user data.
without ever throwing a single warning prompt.
None. All because of one microscopic keystroke error.
That is just wild.
Yeah.
And the source also details how simply misusing the greater than symbol, the redirect, can be instantly catastrophic.
Oh, absolutely.
When you use that symbol to redirect output into a file, the shell prepares the destination first. Before the command even begins to run, the shell opens the target file and truncates its size to 0 bytes.
It wipes it clean to get ready for the new data.
Right. So if you make a mistake in your logic and accidentally redirect a file into itself, the shell empties the file before the command can even read it.
Your data is gone in a microsecond.
Incredible.
But beyond the sheer danger of human error, there's a systemic architectural flaw we have to discuss here.
What's that?
Performance overhead. While shell scripts are incredibly fast for a human to write, they are notoriously slow for a machine to execute compared to native binaries.
I really want to dig into the mechanics of that. Why does a text file running system command struggle so much with execution speed?
It all comes down to process management. Every single time a shell script calls an external command like grep or else or awk entries, the operating system has to perform a fork and exec.
Meaning?
It must pause, allocate new memory space, duplicate the current environment, launch the new program, wait for it to finish, and then tear down the memory space.
Wow, that sounds heavy.
Doing that once is fine. Doing it 10,000 times inside a while loop, that creates massive, crippling computational overhead.
Okay, but the text mentions that pipelines mitigate this issue. How does connecting commands with a pipe change that memory allocation problem?
Well, a pipeline connects the standard output of one command directly to the standard input of the next, strictly in memory.
Okay, so it doesn't have to spin up and tear down as much.
Exactly. Instead of running a program, writing the result to a temporary file on the hard disk, and then launching a second program to read that disk file, pipelines stream the data directly between processes as they run simultaneously.
Oh, that makes sense.
It bypasses the disk entirely, drastically reducing the I/O bottleneck.
Okay, but even with pipelines mitigating performance, the text introduces another massive hurdle. Compatibility.
Ah, yes. The fragmentation.
There is a quote from Larry Wall, the original creator of Perl, who stated, quote, "It's easier to port a shell than a shell script."
It's a brilliant quote.
On the surface, that sounds completely counterintuitive. Porting a massive, complex shell environment to a new operating system should be much harder than just moving a plaintext script file.
It seems counterintuitive until you understand how deeply fragmented the scripting ecosystem actually is.
Give me an example.
Consider Bash, which is arguably the most popular shell in the world. Over the years, Bash has introduced numerous custom extensions and shortcuts that are not part of the strict official POCx6 standard.
The source calls these bashisms, right?
Exactly.
Yeah.
For instance, using double brackets for logical tests is a classic Bashism.
So if a developer writes a script heavily reliant on those double brackets, it runs perfectly on their local Ubuntu machine running Bash.
Yes, but the moment they deploy that script to a server running a minimalist shell like Dash, or maybe an older Korn shell environment,
What happens?
the interpreter sees those double brackets, fails to recognize the syntax, and immediately throws a fatal error.
So the code is incredibly fragile because it relies on an undocumented, non-standard ecosystem to function.
Right. To guarantee a script runs universally across any Unix-like system, a developer really has to intentionally strip away modern conveniences and write in strict, lowest common denominator POSEC-X syntax.
If navigating compatibility across different flavors of Unix is that much of a minefield, how does the broader computing landscape handle automation?
I mean, systems outside of Unix.
Yeah, we have entirely different corporate architectures out there, completely divorced from Unix philosophies.
Well, Apple's Mac OS navigates this pretty easily because underneath the graphical interface, Mac OS is built on a certified Unix foundation.
Oh, right. So it includes a PSecX compliant shell natively, speaking the language right out of the box.
Exactly. But Microsoft Windows is a completely different architectural beast.
Right. It is built on the NT kernel. It doesn't inherently understand Bashisms or PO6 standards.
No, it doesn't. Historically, bridging that gap required immense engineering effort. To achieve interoperability, Windows environments relied on really heavy, complex translation layers.
Like Cygwin.
Yes. Systems like Cygwin or the MKS Toolkit were designed specifically to translate PO6 commands into Windows API calls in real time.
That sounds complicated.
It was. Additionally, Microsoft developed the Windows Script Host, leveraging entirely different engines like VBScript or JScript to manage system automation.
The source also details how these scripting environments utilize the Component Object Model, or COM.
Yes, COM extension.
This is where it gets totally wild to me. Through COM extensions, a plaintext script can actually reach out and directly manipulate graphical applications.
That's pretty incredible.
A script can just launch Microsoft Excel, inject data into specific spreadsheet cells, trigger macros, and save the file, all without any human intervention.
They essentially forced the isolated world of text automation to interact seamlessly with heavy graphical corporate software. This raises an important question, though. Why go through all that monumental effort?
Right, why bother?
Why engineer massive translation layers like Cygwin just to run ancient text-based scripts on a modern Windows architecture?
Because the value is just that high.
Exactly. It is because the value of that glue code is simply too high to ignore. The imperative to automate repetitive tasks, to orchestrate workflows, and to connect disparate, isolated programs into a unified pipeline. That need is universal.
Regardless of the underlying operating system.
Precisely.
So what does this all mean? Let's summarize the terrain we've covered today. We started by demystifying the shebang, that hidden routing mechanism that allows developers to swap out underlying technologies without breaking user workflows.
A brilliant bit of design.
Then we explored how scripts evolved from simple typing shortcuts to the batch job orchestrators that pull humans out of that synchronous waiting game.
Shifting from bricklayer to foreman.
Exactly. We examine their role as the rapid prototyping first draft of software, their fragmented family tree, and, of course, the terrifying, system-wiping power of a single misplaced spacebar tap.
We can't forget that typo.
Never. Understanding the mechanics of a shell script really shifts your relationship with your device. You understand how the components of your operating system are glued together, allowing you to actually command the architecture rather than just consume it.
You transition from a passenger to the architect of your own automated workflows.
Perfectly said.
But before we conclude, I do want to leave you with a final thought, expanding on the unforgiving nature of the command line we discussed earlier.
Okay, I'm intrigued.
We established that shells execute commands with absolute, ruthless literalism. They do exactly what they are told, relying on decades of community folklore and specific POSIX standards to avoid catastrophic errors like that recursive root deletion.
Right. They possess zero common sense. If you tell it to destroy the system, it just complies immediately.
Which brings us to a modern crossroads. Today, we are increasingly relying on artificial intelligence to generate our automation scripts.
Oh, wow.
Large language models can output complex shell logic in milliseconds. But if this scripting environment is so inherently powerful and yet so fragile that a single syntax deviation can wipe a hard drive?
What happens when the AI makes a typo?
Exactly. What happens when the intelligence writing the code lacks the visceral lived experience of a human system administrator? AI does not have the folklore of the Unix community ingrained in its survival instincts.
That is slightly terrifying.
Are we truly ready to hand over the universal remote of our core operating systems to automated generators that might confidently output a script containing a microscopic yet devastating typo?
That is a staggering implication to consider. Trusting an intelligence to build the house, knowing it might accidentally command the bulldozers to level the entire city block.
Exactly.
It definitely changes how you look at that silent, blinking cursor. Thanks for joining us on this deep dive. We'll catch you next time.